Okay, so welcome back to the next lecture here. Today we're going to continue with the Boltzmann's function distribution functions. Today our job will be to find the constant alpha and beta. So let us say that from the Boltzmann function, from the Boltzmann's distribution function, we had n's of j as n times e to the minus alpha minus beta ei, ej. So this is what we basically did last time, right? And this is called the Boltzmann's distribution. So this is the Boltzmann distribution function. Distribution function. Okay, so this lecture here is basically to find, I'll just increase the font size here. Okay, it's basically to find the alpha, the constants, e to the alpha, and beta. So what are these constants if we already have the Boltzmann distribution function, right? So let's say it's not too difficult, so let's see what we can do here. Now, let us say we are summing over the Boltzmann's function over all the j's, okay, all the energy states or the cells. And I can write it like this, right? So summation j and e to the minus alpha dot e to the minus beta ej, and so on. And also we know that summation of j and j is n, right? Sum of all the particles. So this basically becomes n equals to n times summation of j, let me just write like this, e to the minus alpha summation, because it does not have any j dependence, so I can just take it outside, and this is just e to the minus beta ej, right? So rearranging this gives us e to the alpha is simply summation of j e to the minus beta ej, and this is also called q, or we can say this is a partition function. Okay, so this is also called the partition functions. So we'll talk about it in more detail later on, but for now we have the first constant here, e to the alpha is basically summation of j e to the minus beta ej. Okay, now let us understand how to find the second constant, that's the beta. So for this we'll have to assume certain things. Okay, so let me just erase this one, and maybe let's try to find the value of beta. Now imagine that we have a gas, okay, we have a system of gas here, but there are lots and lots of particles. Okay, so there are lots of particles here, and initially it has E as the energy, number of particles is n, and the volume is fixed. Now what we do is we give it a little energy. Okay, so we add up the energy. So we are basically changing the state of the system by adding the energy. So we have some addition of energy, let's say E plus dE chroma, n comma v. Okay, so this is the new state of the system. So because our Boltzmann's distribution function is related with the probability, it has to do with the maximizing the probability, and we also know that entropy is also related to probability. So we use the concept of entropy to find the value of beta. Okay, so now let us consider. Okay, so let us move on with the definition here. So let us consider that we add dE energy, differential energy, to the gas. Okay, so now what it also means is that there will be some shufflings in the number of particles going from one cell to the other cells, right? So it means that there is a change in the number of particles. There's a change in the number of particles in each energy state or each energy levels or cells, right? So we will say that the change that has occurred in cell 1 is dN1, and the change that has occurred in cell 2 or energy level 2 will be dN2, and so on. So remember that Nj was simply n times e to the minus alpha minus beta Ej, right? So what this is saying is, if you add in energy, the number of particles in a certain state will change. Okay, so but you should also remember that we're talking about the system which is in equilibrium again. Okay, so it has already settled down and it's in the equilibrium state, and so this is already considered now. So because there is a change in energy, there's some energy added, the number of particles having certain energy E1 will change. Okay, so let's account that change to be Dn and so on, Dn2, Dn3, and so on. Now, from the thermodynamics perspective, we know that the internal increase in the internal energy increase in the internal energy at a constant volume is simply this, right? So dq, we basically represent the amount of heat added as dq, which is also dE to be TdS, right? So this is a basic differential formula to account for the increase in the internal energy at a constant volume. Okay, now this is equation 1. Let's put that as equation 1 because we will have to compare it with this to get our value for the constants of beta. Okay, now we said that this was the change in the number. Okay, what about the change in the energy state? Of course, the energy state also changes, right? I mean, yes, the energy content of each cell do change, and because it's proportional to the number of particles in it, right? So now let's account that change as dE. Now, so we can just write dE as epsilon dN1, right? Because epsilon 1 is the energy state of the first cell, energy state of the energy of the second cell is E2, and the energy of that particular cell, when there is a change, is that, and so on. So I can write this as summation of I, EI, okay, EI, dNI, right? Now, I is just a dummy variable, so you could replace it by any variable you want. So let us say I represent it by I here, and I goes from 1 to how much ever cells that we have divided it to. Okay, so this is also the important equation that we needed. Okay, so let us say this is equation 2, and now let's use the Boltzmann's entropy formula to come up with the value for the beta constant. Okay, so let's move on to the next part then. So let's create a new whiteboard here. Okay, so I'm creating a new whiteboard here. Okay, so we know that the entropy of a system is given by K log of omega, right? So where omega is the thermodynamical probability. Now it is basically, omega is not a probability, okay, but it's a thermodynamical probability in a sense, like you could calculate the probability of certain state, microstates and all, using omega. Basically, omega is the number of microstates in a given macrostate. Okay, and this is the Boltzmann's entropy formula, and also we noted in the last lecture that we could write log omega as n log n minus n. Oops, I'll just write down the formula directly. Okay, so simplifying everything, so this can be written as ni log e's of ni. So you could have written just ln ni, but I just choose to write log e. Okay, now what if I take the ds now? I'm computing a change in ds here, so then k is a constant. Now I have to differentiate this one, right? So log of omega, right? So then I can write this as k. When I want to do this calculations here, I know for the fact that the change in the particle, overall particle, is 0. So this, the first part simply becomes 0, right? Minus. Now in this case, you have to find differentials between the two terms. So it just becomes summation I and I. So it's d log e and I plus log e and I d and I, right? So this is the differential change. Now if you look at the term, okay, if you look at the simplification here, then this simply becomes k minus k and summation I and I. So I have to find a differential in this, so why not just differentiate it with respect to ni, and let's check what we have here. So this is dni, right, plus excuse me, now this becomes minus, I just multiply both sides by minus, and then this just becomes k summation I and log e and I d and I, right? I hope it's clear. Now d log e and I by d and I is just 1 by ni, so this just becomes k summation of I d and I, right? So n I and I gets cancelled, and that's the thing, and this becomes simply k summation of I log of E and I d and I, right? So we then have the change in entropy ds for a system where we have considered as the entropy to be the function of a thermodynamical probability to be this one. Okay. Now, as we know, we've already calculated we've already found out the distribution function, right? Boltzmann's distribution function, where ni was n times e to the minus alpha minus beta ei. So we'll just substitute the values here now. Okay, so we just substitute the values here, and we will continue with the thing. So I'll just erase this one now. Okay, so I'm erasing this part here. The only thing we have to do now is to substitute and then to compare. Okay. Now, our simplification then gives us this. Now, summation of I d and I is just dn, right? So is there a change in total number of particles? No. So this is 0. So this number out here is simply 0, right? So this gives us 0. The first part is then 0 minus k, and let us substitute the ni. Okay, so this just becomes, just for simplicity, I'll write ln here now, and this becomes n e to the minus alpha minus beta ei, and then dni, like this. Okay, now remember this one because this will be used again. So now this simply gives us minus of k summation of I. Now you can just use the log rule here. So I can write this as log ln n plus ln e to the minus alpha plus ln e to the minus beta ei, then multiplied with tni, right? So then this simply gives me summation of I ln n dni plus summation k, excuse me. I'll write all of these as one term, so I don't have to write negative term. So this just becomes summation of I, so summation of I e to the minus alpha is just minus alpha here, times dni, and minus so beta ei dni. So this is the summation. I've missed out the summation. So this is basically the simplification of that. Okay, now let me just erase this one here, and let us continue here. So again, ln n is just a constant because there's a fixed number of particles. So summation of I dni, again, it's 0. So let me just write it so that you understand what I'm saying. So first term is just ln n, summation of I dni, 9 plus alpha summation of I k, sorry, so I'll just write k outside, summation of I dni, and plus summation of k, excuse me, I'll just write all the constant outside, beta summation of I ei dni. Okay, So this is a change in the entropy. Now this is 0 now, right? I just said that this is 0 in the previous thing, and so this simply gives you ds as kb summation of I ei dni. Okay, now it's very easy to also note down. At the very beginning, I also told you that summation of ni ei was just E, right? That's the total energy. So if you look at the change in the energy, so if you just find a differential of this, just equates to summation of I ei dni, right? So de, so k beta is just, sorry, ds is just k beta de. So this is the thing that we used. Just found the differential of the thing. Now what we do is basically try to compare the equation now. Okay, so we just compare the equation now. So now we have two equations. So ds as kb de, and from the first equation we also had ds as 1 over t de, right? So when you compare these two equations here, so when you compare this and this, the coefficients should be same, right? So then this just gives you k beta as 1 over t, therefore beta is 1 over k t. Okay, so this is then how we find the constant beta in the Boltzmann's distribution function. So now let's rewrite the formula, the Boltzmann's distribution formula, and let's check out what we can have. So ni is then basically n times e to the minus alpha dot e to the minus ei over kt, right? Because now beta is 1 over kt, so I just write down the thing. We also have the values of e to the minus alpha, right? So e to the minus alpha is just 1 over summation of I e to the minus ei over kt. And I also told you that it's a partition functions. So this expression here, I can write it as ni over n equals to e to the minus ei kt over kt divided by summation of I e to the minus ei over kt. Now this term here is also called a probability. I mean, if you remember, I said at the very last lecture, I said that this was the probability of a particle having energy ei. Okay, so this is then the equation that we have. Okay, so if I have to write what is p epsilon pe, then we can write pe I as the probability that a molecule will possess energy Ej. Okay, now remember we said that there are cells. Okay, in that cells there are different particles, different numbers of particles. Now how can you how is the probability found if you want to check that certain number of particles should be in this particular energy state. So it's done by the Boltzmann's equation here. So if you want to find the probability of particle being in certain energy state, then you use this one. And this is very, very important formula. And okay, so I think we're done for today. We'll do this much. I hope to see you in the next class, and we'll come up with the topic on the Rayleigh's equations, and talk about the Planck's formula, and so on. Okay, thank you.